We're all yours.
All right. Well, I'm Brian Carter. I'm an adjunct instructor at Pasadena City College and Mount San Antonio College in physics. My background's actually more in like chemical physics and biophysics than stuff like astronomy. So there's going to be a possibility that I say something a little bit wrong. If you happen to know better than me, feel free to jump in. Um, Let me see. I'm involved in this stuff because I'm really into astrophotography. I haven't had time to do it since COVID started because classes at the schools have been kind of nuts. But I've learned how to do a lot of interesting things like this sort of stuff and putting myself in it. So I'll be talking tonight a bit about ultimately the three-body problem and honestly, more specifically, kind of the Lagrange solution to it. The talk has evolved quite a bit as I've been trying to work on it. So ready to start? We'll see. I haven't actually tried advancing slides this way, so it's going to be interesting. All right. So the first thing I wanted to talk about is just a brief reminder of the gravitational force, or at least Newtonian gravitation. We're not going to try and deal with anything that comes from general relativity, like time dilation or anything like that. So this is probably a different way of writing it down than you may have seen before. This is taking the position at, well, the zero position as the point where the two r's are together and coming out to the two masses, vector r1 position, vector r2 position. Reason why this is, I'm saying it's different, is normally gravitation, you'd think it's g m1 m2 over r squared. This way of writing it gives you the direction in a fairly precise way that when we start dealing with the three-body problem will be useful for us. It turns out to be the same kind of thing. Normally this would be m1 m2 over r squared in the radial direction or the anti-radial direction, depending on the object you're looking at. This on top is being divided by its magnitude. Since they have the same length, it doesn't change the size of the gravitational force at all. It still has the same size it would if it was gmm over r squared. All right. So particularly, we're looking at problems where we can solve this equation for the motion of an object. And if you've studied any physics, you know that F equals ma. So we could write this force equal to the mass of the object times its acceleration. All right. I also wanted to remind you about Kepler's laws because, at least for the two-body problem, they are generally applicable. Kepler's laws were the planets orbit a sun in ellipses with the sun at one focus. The planets sweep out equal areas in equal times, and the period of the orbit squared is proportional to the semi-major axis cubed. And I will be referencing this equation about how the period squared depends on the semi-major axis very briefly when we're talking about some of the Lagrange points, because there's interesting things that happen there. All right. Is there a question? I just thought I heard something. All right. So you could actually do a one-body problem. When one mass is much larger than the other, you can solve the behavior of the lightweight object using the previous formula, just assuming that the larger mass is at the center of your coordinate system, then that it never really moves anywhere. And that's probably the easiest case to solve. If you do that, it leads very naturally to Kepler's laws above. But you might wonder what happens if you have two masses that are much closer in size, something like perhaps a binary star system. And when the masses are closer in size, you can still solve it using the same general idea as the one-body problem, but you need to reframe the question. You have to change the way you're looking at the problem. It does turn out it still results in behavior that broadly follows Kepler's laws. So you still get elliptical orbits, but now they're elliptical orbits around the center of mass of the common system. I think I'm going way too fast, so please slow me down if you need to. let's see. So here, if you had two masses, if these masses are now similar, you can look at this white point in the middle, which is the center of mass, and you can calculate what happens around that center of mass. And I don't really go into any of the math on this, so I'm kind of asking you to trust me, it comes out with similar equations. But since there are no external forces acting on these two objects, the center of mass will continue to move however it was at the beginning. So if you know the initial velocity and you know the initial position of the objects, you could calculate the motion of the center of mass and it will be constant. It will continue to move in whatever direction it may or may not have been moving to begin with. And then you can look at how the motion of the objects is around that point. This actually lets you simplify the equations a bit, and you can solve it. I'm repeating myself. You can solve it the same way you solved the original equation for the central body problem, more or less. Difference is you end up with the reduced mass in there instead of the mass of one of the objects. But it does turn out that the equations result in elliptical orbits. This time not with the sun at one focus, but with the center of mass point at one focus. So all of these have the exact solutions. You can get down to a very exact equation, and you do get the equation of an ellipse. But that's where things start to get interesting. Two objects works really easily, but what happens when you include the third? It doesn't seem inherently obvious that that would be tremendously harder. You might think it's just, one more object. But it will turn out that the equations get a lot more interesting. Right. So for the three-body problem, you can write down the acceleration of each of the bodies, which would be a second-order differential equation. And you end up with three vector equations. Since these are vectors in a three-dimensional space, each one actually represents three separate differential equations. We essentially go from having one equation or two equations or three equations up to having a total of 9 here. So just adding one more object, we've really increased the difficulty in what we have to accomplish. We can recast these equations, which are second-order differential equations, into 18 first-order differential equations. But if you're solving 18 equations, you have 18 parameters that you're going to have to fill in. And it turns out you can only get 11 or 12 from the initial conditions of the objects really easily. You're stuck for information. So it turns out that what we usually would say about a problem like this, it has no closed form solution. And that idea of a closed form solution, it turns out it's a lot fuzzier than I thought when I started researching. Saying that something is not generally solvable, it's not solvable in a closed form, is really just saying that you can't write a finite solution made up of very simple functions, the sort of thing you think of like a quadratic or a sinusoid or things like that. And the finite statement is precise. It does turn out that you can write a general solution that is, what's the word I'm looking for? An infinite series. The infinite series turns out to converge very slowly, however, so it's not considered terribly useful generally. It's also a little disingenuous to say it's not solvable at all, because you can actually attack it with numeric methods. In the general case, you can take the initial positions and initial velocities, and you can do a very short time step forward in time, and essentially assume that for that moment, the acceleration has a constant value or a simple form. You can use the general equations of motion that you may have learned in a physics class. And then you use the results of that as your initial conditions for the next very short time step, and you can propagate it forward. The issue is you find it's very, very sensitive to the initial conditions. A simple simulation where you're trying to handle, here's the sun, here's the earth, and here's the moon orbiting the earth. Just by changing the speed of the moon a slight bit, you can end up accidentally ejecting it. One of my students many years ago was trying to do a VPython simulation that was initially a two-body one. And he tried to add the moon in, and we were actually struggling to get it to work in a Cartesian coordinate system without, after an orbit or two, ejecting the moon. So probably our time step could have stood to be shorter there. All right. It does turn out you can solve it in a closed form, relatively simple functions, if you choose to use very specific cases. And at this point, there are thousands of special cases that people have discovered. Reading about that, well, that's very interesting in and of itself, I suppose, but mathematics, if I'm being blunt, gets a little bit beyond where my level is at the moment after 10 years of teaching first and second year physics. Some of the more interesting ones would be setting up a figure-8 orbit with equal masses where all three masses follow the same figure-8 orbit. I think that one was discovered in 1993. Since then, various researchers have come up with techniques for finding more of them using computer simulations or computational methods at least. All right. So since it's not generally solvable except using a numeric method, which is pretty much what everyone does to solve this, there are special cases that do solve into simple results, and the most interesting of those are probably the ones that result in the Lagrange points. So we're actually going to segue off and focus primarily on the Lagrange points from this point on. Let me see. I ran out of time to do this. I was hoping to get some videos from a computer game which has a mod that implements in-body physics using numeric methods to figure out where planets and spacecraft would be. Alas, I did run out of time for that, but big simulations that try and simulate an entire solar system will actually go even beyond the three-body problem and add in many bodies, and then calculate using the same kind of equations written above, using numeric methods to find how things evolve over time. All right. So closed form solutions do exist for specific cases. Said before, many such cases have now been discovered, thousands falling into various families of solutions. And we're going to focus on the special cases found by Lagrange and Euler. In researching the Lagrange points, I was very interested to find out that the first three of them were actually discovered previously by Euler, which reminded me of something I'd been told many years ago. I can't remember if it was a math student taking my class or a math professor who told me this, but turns out many things in mathematics are named for the first person to discover them after Euler. So he was apparently quite the prolific mathematician. All right. So I'm going to call all of this Lagrange's solution, even though, as I've said previously, the first three were discovered by Euler. It appears all the orbits are assumed circular for this, and it's also assumed that the third mass is negligible. It does turn out that two of the Lagrange solutions only really apply if the mass ratio between the heavy masses is sufficiently large, and that ratio appears to be somewhere around 25. The special cases essentially amount to when the three masses make a straight line and remain in a straight line throughout the entire orbit. And when the orbits of the three masses fall on an equilateral triangle. So here's a diagram taken from a NASA page showing the 5 Lagrange points. The L1 point would be in between the most massive body towards the center of the system and the second massive body. It is essentially the place where the forces between those two bodies would cancel out. The L2 point lies beyond the second massive object. The L3 point lies exactly opposite the second mass, or the second most massive object. These are the three that are collinear and would orbit with exactly the same period. So the L1, L2, and L3 points would all take 1 year to travel all the way around in a circle, if we're talking about the Earth-Sun system, for instance. And if you think about how Kepler's laws said things work, this might seem a little surprising at first, because normally when you're thinking about Kepler's laws, just a two-body system, the semi-major axis, the distance between the center body and the body you're looking at, determines the period. And you would expect that with the sun being basically at the center, or the massive body being at the center, that the L1 point being closer in would actually orbit faster. But you can effectively think like the Earth is tugging the opposite direction and reducing the effective mass of the sun. So if you look back at the equation we had before, I'm actually going to cheat a bit here, and if I can find it, I hope things aren't jumping around for everyone with this. There we are. That'll let me do this. The equation looked something like the period squared is equal to g times the central mass over 4 pi squared times the semi-major axis cubed, which means it does depend on the central mass. So we can essentially kind of cheat the situation by having another object further out that's tugging it the other way and effectively reduce the mass. On the other side of things, if you look at the L2 point, it's further out. So you'd normally expect it to have a period that would be longer than an Earth year. But we're effectively increasing the mass of the central body by having another one in between. So again, same formula, if we're effectively increasing the mass, we can drag the period back to a smaller value closer to what we're expecting. Or I feel like I've got something upside down here. Good grief, did I write the equation upside down earlier? Pardon me a moment. Nope, that's actually okay. All right, I wanted to be really sure. Okay. Right, the L4 and L5 points are a bit harder to understand what's going on, so we're going to change the point of view on this. So far, we've kind of talked in the language of forces. There we go. You can also think about what's happening with the potential energy to understand how an object would move. And this right here is just a plot of the gravitational potential around a small uniform around a uniform spherical body. And you can see it's coming up towards some constant value, and it drops as you come in towards the central body. There's a principle in physics where you can take the potential energy surface, and if you look at the slope of it, the force is always opposite sign of the slope. So here, if you imagine starting at the central point, you can see there's a positive slope as you come up out of this potential well, which means there's a center pointing force. The force will actually be in the negative direction. So as you move radially outward, the slope is positive, which will indicate an inward pointing force exists. All right, so let's take a look at the sort of potentials that get drawn for the Lagrange case. This is the sort of thing you see when you try and look up what does the potential energy look like around the two massive bodies when you do a plot of the energy for finding the Lagrange points. Pardon me. And if we look at this, it's actually sort of curious looking because you're coming up out of a well, you see contour plots closer together. This is basically the same idea as reading a topographic map. So we're coming uphill and we reach a peak. And then this is the interesting part. It shows us falling downhill as we go away. So you might wonder, why doesn't it look like the same plot as the previous one where it comes up towards a constant value? It turns out when these plots are made, you're actually taking the centripetal force and bringing it inside as the centrifugal force and plotting what happens with those two forces acting together. Let me see if I can explain that a little bit better. First, it's kind of a weird idea. I just said we're going to use the centrifugal force, and most of you have probably learned the centrifugal force is the fictitious force. The centripetal force is the real thing that happens. Well, we're essentially trying to take the rotational motion and get rid of it so we don't have to think about how things are moving around. And the L1, L2, L3, L4 points maintain a constant spacing and the Earth doesn't appear to move. So we're going to take and bring that to the other side of our force equation. So XKCD is this wonderful comic where they do really nerdy stuff. And I have to admit, as a physics professor, we do have a tendency to say, no, 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 that's a fictitious force, forget about it, it's just an artifact. And this makes a very good point that you don't have to treat it as an artifact. So here it's got James Bond strapped to a centrifuge, and the bad guy is saying, how do you like my centrifuge, Mr. Bond? When I throw the lever, you will feel centrifugal force crush every bone in your body. You mean centripetal force. There's no such thing as centrifugal force. A laughable claim, Mr. Bond, perpetuated by overzealous teachers of science. Simply construct Newton's laws in a rotating system and you will see a centrifugal force term appear plain as day. Guilty of telling my students this sort of stuff. Come now, do you really expect me to do coordinate substitution in my head while strapped to a centrifuge? No, Mr. Bond, I expect you to die. All right, so how are we going to deal with this? Well, we're going to take the centrifugal force inside, and the result of it is the following. As you move away along this surface, you continue to have the same rotational speed that you had before. That means for the new orbit further out, you are going too fast to stay in that orbit. You're going to tend to slip further out. And the centrifugal force is going to handle that and cause you to fly away from the center of the system because you are now farther away but rotating at the same speed. You have too much energy. You are going to get flung towards the outside of the system. Okay, so this view is a little bit easier to follow what the contour plots are showing. They show the L4 and L5 points are up at local maximas. And they show the L3, L1, and L2 points are all falling in saddle points. Okay, well, if you remember what I said before, the force is going to go in a particular direction. If the L1 point, if you're at the L1 point and you started to come a little bit further in, you'd have the same speed, you'd now be going a little bit too slow, and you would expect a force. Also, the way this is plotted, it's got that positive curve coming up, it's got the positive slope, you'd expect a force towards the middle dragging you in. If you slide a little bit further out towards the Earth or the second heavy body, you'd expect it to get dragged in that direction because now you've got a negative slope indicating a force in the positive direction. And we can look at all these points, and what they all seem to be saying is, wait, if we actually sit something here, yes, it will sit nicely there, but if you bump it the slightest bit, it should go flying off either towards the outside or the inside. So that's kind of interesting. That suggests all 5 of these points would be unstable equilibrium. But in fact, the L4 and L5 points are stated to be relatively stable. You can orbit the L4 and L5 points for a very long time. If you've ever heard of the Trojan asteroids, there's pools of asteroids that lead Jupiter around its orbit and follow Jupiter around its orbit, and they sit roughly near these L4, L5 points. They sit there over long periods of time, so clearly the orbits are, as stated, stable. So now we need to try and understand, why are L4 and L5 stable places, places where you could put something and it should stay there for a very, very long time?
Which L point is Webb going to?
Webb is going to the L2 point.
Okay.
So we're actually going to get to the L1, L2, L3 points after the L4, L5, because it's a little bit harder to understand what happens there. Well, maybe not. I certainly, when I was making this, thought that the L4 and L5 were a bit easier to understand, but that's probably because it clicked first. But we'll talk about L4 and L5, and then we'll come back around and talk about L1, L2, and L3. But are there any questions at the moment? I'm hoping I didn't use too little math for once. I kind of threw all the math out. Okay, then let's see. All right, so the 4th and 5th points allow for stable orbits, which isn't obvious from our energy plot. It suggests they're local maximas and they should go flying away forever. It turns out the reason why you can stay there is the Coriolis force. Yet another one of those fictitious forces that only appears when you're in an accelerated reference frame. But we just took and specifically constructed everything, imagining that in essence, the Earth and Sun and the L1 through L5 points aren't going anywhere. But of course, they actually are rotating. The entire picture would be physically rotating around with a period of, if we're talking about the Earth-Sun, 1 year. So as you start to move away, you experience the Coriolis force. And a way of understanding that is, imagine you're on a merry-go-round that's rotating, and you try and throw an object to someone on the opposite side. Well, once the object leaves your hand, it's not really under the influence of any sideways forces anymore, which means it's going to go in a literal straight line direction, while the merry-go-round continues to rotate under it. And if we go back to this, the same thing would happen. If you started to leave the L4 point going radially outward, then the entire picture here is effectively rotating underneath you as you attempt to go in a straight line direction away. And you appear to curve off to the side. That might be hard to imagine, but I have a picture here, or video here, where I did exactly that. I wish this one had the slow motion capability, but you'll see the ball go off towards the side. So this is a view from inside the rotating reference frame. This would be a view directly from our picture of what the energy surface looks like. And as the object moves radially outward, it appears to experience a force that curves it over towards the side. And that's actually what will happen inside of these regions. You're still in a relatively flat spot near your local maximum. As you move away, you'll experience curve due to the Coriolis force that'll tend to make you orbit around the L4 point. No, it's not a simple looking orbit. It really kind of stretches out and back. It seems like it follows the contours. But you will stay within this contour for a very, very long time, more or less orbiting around the L4 or similarly the L5 point. Okay, are there any questions about L4 and L5?
Now around Earth, we can find, just like Jupiter, we can find trailing asteroids or something
You
like
know,
that.
I looked into that a little bit, and I think there may have been some detected, yes, but here's the interesting one. The mass difference between the Earth and the Moon is good enough that it's kind of a stable place for the L4 and L5. So if you look at the Earth-Moon system, the L4 and L5 points near the Earth-Moon actually collect dust, and there is an enrichment of dust at those points. So yeah, these things do apply. Um, so yeah.
I was thinking that when we finally have a manned mission to Mars,
Mhm.
you would want at least some sort of communications craft in one of those, because
Yes.
when Mars gets on the other side of the sun, you're going to still want to talk to the guys.
Yes, I was thinking about that as I was looking at all of these Lagrange points, and the L4 and L5 definitely look like they'd be good places to throw some kind of communication satellite. They have the same period as the Earth. Uh, their orbits are going to be kind of weird around the L4 and L5 points, so I don't know how much maneuvering fuel it would really take, but it does seem like that's the points where you'd want to sit stuff like that. Apparently, science fiction novels like to put hidden planets at the L3 point, which is coming up, which is kind of interesting. That's the one that's on the exact opposite side of the sun from us. Uh, Unfortunately, as we'll see, those are points of unstable equilibrium. Unlike the L4 and L5 points, you can linger there, but without something to kind of nudge you back in, you're going to tend to fly away from it. Okay. You know, it's dawning on me, I should have duplicated one particular slide and put it in 3 different places. I did run through this earlier, but I somehow did not think to do that. All right. So the L1, L2, and L3 points are unstable, at least over the long term. You can stay there for some amount of time. I think when I was looking this up, the L1 point, it's something like 23 days that you can kind of set there before you have to do maneuvering to keep yourself there. The interesting thing is, like the L4 and L5 point, you would expect there to be a Coriolis force as you move away from the point. But those saddles on the sides end up doing something interesting to this. All right, so if you look at the L1 point, you can see that along one side, it's curved kind of like a parabola face down, but on the other side, it's curved more like a parabola face up. You see the same thing a little bit more weakly with the L3, but just as strongly, or just about, with the L2 point. So I borrowed this, and I'm not sure how much help it'll be. This is a literal saddle shape. And you can see how it's curved in one direction. And as you rotate it, kind of curved the other way. So if you are sitting at the center of the saddle point here, and you begin to move towards the central body forward or towards the second body backward, you do start to experience a Coriolis force. But as the Coriolis force tries to bend you towards the side, the actual potentials due to the masses already present and due to the centrifugal force will squeeze back against that to some degree, and it prevents it from making quite the full complete orbits that we get in the case of L4 and L5. You kind of get trapped between these sides, and it tends to squeeze you down the well. So over time, those points end up being unstable points. Oops. Oops, oops. Okay. All right, so what are the interests of these different points? Well, L4 and L5, they're pretty far away from Earth because you're 60 degrees ahead of the Earth in its orbit and 60 degrees behind the Earth in its orbit. So could be a really good place maybe to put a communication satellite as we're trying to deal with talking to astronauts who are getting ever further away. Beyond that, I'm not sure if it has a particular human use, but of course it has the cool use of it tends to collect things like dust and small rocky bodies. The L1, L2, and L3 points. Well, L1 and L2 have particularly L1, has a fairly obvious use. If I come back to one of these pictures, the L1 point remains forever in between our lighter body and our heavier central body. So you can put a satellite that always faces the sun right at this point. If you want to watch the sun, that is a pretty good place to put it, because we don't have to deal with it being in low Earth orbit and getting eclipsed from time to time. We don't have to deal with it being in a sun synchronous orbit. We can just put it nice and far away from the Earth. The Earth won't particularly influence it outside of obviously it being a Lagrange point. And you can just sit there and stare at the sun and shoot your data straight back to the Earth. The L2 point, a little bit the opposite. So if you sit things at the L2 point, they're still relatively close to the Earth. They still orbit with the same period as the Earth. Not being close to the Earth, you don't have to deal with them, getting light from the Earth or heat from the Earth. For the Webb telescope, I'm suspecting that that may actually have something to do with it, is getting away from just the warming effect of being near a body radiating its heat back out. But you also, if you orbit in the right way, can get a clear view of the sun at all times. You'd think, yes, you're in the shadow of the Earth, but the shadow of the Earth is actually relatively small at that distance, I would say. You could potentially pass through it, but you can orbit in such a way that you would be going out of the plane here and you can keep the sun in view. And it also lets you easily just point yourself away from both the sun and the Earth at all times and view large portions of the sky. So there actually have been a few instrumental missions put there. I should have written the list down. I'm trying to remember now. Gosh, what's the name of the one we used to discover all the planets? I'm pretty sure that one's out there at L2.
TESS?
No, TESS is actually in an Earth orbit. It's just kind of an eccentric one.
I think that's Kepler, and Kepler was in an Earth
Kepler.
much like
Kepler's in an Earth trailing one. Okay.
Yeah.
All right. I don't know. There's at least one instrument mission that's out there right now, and Webb, of course, is scheduled to go out to the L2 point. The interesting one is, well, what would you do with L3? Well, okay, that seems like it would be a pain in the butt to get to. And worse, we can't communicate with it because it's on the opposite side of the sun from us. So unless we already have something at L4 or L5 to act as a communication relay, having something there doesn't seem that interesting. You could potentially put another satellite there, I suppose, looking at the sun to see what's happening on the other side, but the sun rotates on its axis pretty fast, relatively speaking. So we see all of it in a relatively short period. And we're most concerned about what's headed at us right now. So maybe someday we'd want something there just in case we're worried about coronal mass ejection headed from Mars, for instance. But, yeah. Okay. Well, hopefully I've shown you something interesting, but I think that is going to be it. So the L1 point is cool because it's always between the Earth and the sun, so the distance will stay constant, and it's perfect for solar observation. You can just sit stuff there staring at the sun, have the Earth behind it, send the data back. L2, it's reasonably close to Earth, always in a constant place, more or less, as long as you steer yourself to stay orbiting it. Has a view of the sun for solar power, and has a nice clear view of a lot of the sky. Okay. If anyone wants to know what the Coriolis force looks like from the exterior perspective, I have a video of that in case anybody asked for it. But that is actually everything I had to talk about.
You were talking about I was thinking about the cycler that goes like there, this is still science fiction in a way because they haven't created a cycler to go from here to the moon or from here to Mars. But in Buzz Aldrin's last book, he was talking a lot about having a Mars cycler. And it's basically you'd go to to Mars, and then go to L2 beyond that or whatever. So it sort of does a figure 8 when it gets to Mars and then comes back, kind of thing. And same thing for the moon.
Yeah.
But I would think that the calculations for that would always, while it's close, you'd always have to be doing updates, just because the moon's not uniform or neither is the Earth. It's
Yes. I didn't talk about that at all, but the fact that objects are not uniform when you're close to them really does mess with things a lot.
Yeah. So
it's because the Earth is an oblate spheroid that you can even get a sun-synchronous orbit. If we didn't have that extra weight around the middle, you wouldn't be able to take advantage of it to twist your spacecraft around. Thank you, Scott Manley, for teaching me about that. That, by the way, is a YouTuber who talks about a lot of space stuff, including different orbits.
Yes.
And he talked about the cycler too, and I can't mentally remember what the orbit ends up looking like. But yeah, you end up having to, fly up and join it while it's on its path and fly back. But it just keeps going around forever between the two bodies. I don't remember how long it takes, though. It's pretty long, if I remember right, for the full cycle.
You mean cycling between the Earth and Mars?
Yeah.
I didn't think you could do that, but I should look into that.
Yeah, I have Aldrin's book. I see what the name of it is here.
Well, this is one of those things. I think Scott Manley talked about it as an Earth-Mars thing, but the Earth-Moon, that makes a lot more sense, and it's a much shorter path. So.
Oh, yeah.
Oh, yeah. Well, Buzz Aldrin.
That's kind of a ridiculous thing to say. Oh, it's a lot shorter. Yeah, the moon is just, light seconds away. Mars, good grief.
Well, Mars is so far away, it just seems that the Earth isn't going to be in the right spot, because the Earth moves a lot faster than Mars. There's no collinear.
Yeah, I think it ends up being some weird every 2 cycles thing. It's something weird.
Because oppositions are about 26 months apart.
Right.
And we time all our Mars missions for opposition.
So we can do all of our calculations to L1 and L2, considering the mass of our spacecraft is so infinitesimal as compared to the Earth and the moon.
Pretty much every spacecraft. I mean, every spacecraft.
Oh, yeah.
It's only if you were going to an asteroid, maybe you'd want to even think about it, I'd imagine.
The Voyager spacecraft slowed down Jupiter as it got its gravity assist, but if you want to try and figure out how much it slowed Jupiter by, be my guest.
Interestingly, I asked someone about that once. Okay, so when we're doing all of this stuff with gravitation, we always assume center body. And of course, if you're looking at center body, you can't steal any energy away from it and do gravity assist. So how did that work? And it was really funny because the person I asked this question said, well, you don't do it in the frame of reference of Jupiter, you do it in the frame of reference of the sun. Oh, okay, so now it makes sense. You can slow Jupiter down by speeding up your spacecraft.
Sometimes when I tell my students about this and they say, well, could we actually affect the orbit of Jupiter? And we could throw the Earth past Jupiter and get a gravitational assist, and it still wouldn't have much effect on Jupiter's orbit. So.
Yeah.
Only in theory.
We'd probably kick the Galilean moons out, considering how sensitive these things tend to be, but that would probably take years.
Yeah, I don't know. Actually, those Galilean moons are in a pretty tight resonance there. They actually are holding themselves in place pretty effectively.
Yeah, you have to work hard to pull that off.
Hey, David, I like your background.
Oh yeah, gotta be in an appropriate location here.
I suppose I can stop sharing unless anybody wants to see that other video, but it's just to do with Coriolis force, not with Lagrange
Sure.
points. What? You're curious about that one?
I'd like to see it.
Okay. So let's see, the view from outside. So this is showing the stationary view with the rotating reference frame, and the ball is functionally coming straight at us the whole time. But you can see the reference frame that's rotating rotates underneath it. I wonder how hard it is to restart this. Oops, go back. So yeah, right at the moment when it leaves, it's headed more or less this way. It does get bent a little bit due to friction with the table, but it basically comes straight at us as the table rotates underneath it. And if I go back to this one, you can see the opposite view where from the view on the table, it looks very clearly like the ball is getting curved off to the side, forced off to the side by some mysterious force. But of course, what's really happening is it's just going straight and the reference frame itself is turning underneath it.
They showed a thing on the ISS where they actually had a fairly large clear box, and they had water squirt out, and it went straight, and it was just a little. But then what they did was they spun the box, and then they're saying, now just think that if you were on a centrifuge inside, like they always show, like on The Martian and stuff, like if they were in a spinning, or 2001 they were in a spinning, and the guy goes, now if he's pouring his coffee down into his cup, he can't have the coffee cup directly underneath, because it has the coffee pot, is at a different circle than the coffee cup, and so it's going to turn, and so that was sort of a neat thing that they were trying to show something like that. But in the ISS, you don't have a lot of space, so you can't do it too well in a box.
Yeah.
You're in free fall on the ISS, so you'd have a hard time pouring coffee no matter what you did.
Yeah,
that's true.
Yeah, that's like when they had to spin the box, theoretically. But anyway, it was more of a ball than a box. But yeah, but the gist is the same.
So one other fun application of these Lagrange points is the co-orbital moons of Saturn, where you've got basically bodies that are in almost the same orbit, Janus and Epimetheus, for example. And so they are in so one of them is basically effectively oscillating around the L3, and the other one is doing a horseshoe orbit around the other, around the L, the L4, L5, and L3 for the first one. So you have this this complex combination of these
I see.
one going around 3 of the Lagrange points for the other moon. And then when they get close to each other, which they do every so often, because they're slightly different orbital distances, that's when the gravitational pull of the two moons causes them to basically switch places in terms of their distance from Saturn. And then that's how they then are able to separate out again. So they never actually pass each other. They just get close.
But they don't switch orbits, like one goes into the other one's orbit and one that doesn't happen.
They switch distances so that
Yeah.
basically, so if you look at it in the rotating frame, as I say, one of them is just oscillating back and forth on one side of the planet. The other one is doing this long horseshoe shaped thing going up, the
Mhm.
smaller one basically does this much longer orbit past three of the Lagrange points.
Interesting.
No idea the Lagrange points were related to that. I hadn't come across that. That's cool.
Yeah, I didn't know that either.
Yeah, that's sort of it. Once you move out of the central potential, then you get into the you get these either you get the tadpole orbits like the Trojans are in, or the horseshoe orbits for these longer for things that basically if you took a Trojan asteroid and kicked it a little further away from the Lagrange point, it would go into a horseshoe orbit instead. And then it would be switching back and forth between the past three of the Lagrange points.
So there are quasi moons, like I know the Earth has one or two and Venus has ones that sort of share and sort of don't share the orbit of the planet. I think they're temporary. I don't think they're permanent. So what kind of orbit are they in?
I think they're probably in horseshoe orbits too. Is that what you saw? It's been a long time since I've looked at that, but
Haven't really, I didn't bother to look those up. I'm sorry.
Well,
I know about the various moons that we get that kind of stick around for a while and then disappear, but I haven't looked into that.
there's a couple of different options. I mean, there's the ones that are basically in these kind of horseshoe orbits. You can also get things that are actually orbiting a planet temporarily.
Mhm.
And so that's things like, well, Shoemaker-Levy did that before it hit Jupiter. It orbited around Jupiter for something like a century. In this very long, because it had been captured into there's a little gap in the gravitational well there. It was able to go in and have this very long orbit, 12-year orbit around Jupiter. And if it hadn't have crashed into the planet, it could easily have been ejected back out of the same hole at some later date. But
Well, it's my pet argument, whether it's right or not, I think it's fun, that since the Earth has at least one, maybe two quasi moons, it has failed to clear the neighborhood around its orbit and therefore it's not a planet, according to the definition from the IAU. And so I think they need to work on that. Semantics, I know.
now, back when I was actually a long time ago, when I was doing my thesis research, we were actually doing simulations on the three-body problem, just like that. And one of the things we found were these kind of temporary orbits, and we came to the conclusion that probably at any one time, Jupiter probably has at least one cometary type body or asteroidal type body that's probably sitting in some long distance orbit at around the 1 kilometer size, orbiting around the planet. But they're hard to see because they're way out there, and most of the time they're not that close to the planet. But we sort of argued back in 92, 93 that we thought we figured we looked hard enough, we should be able to find these things out there.
So
Yeah.
the Lagrange point where Webb will be means that every 20 days or so they need to adjust the orbit.
The L1 is the one that's like 23. I didn't see a specific number for the L2. I wouldn't be surprised if it's slightly different.
And it's solar powered, right?
Yep, I believe
James
so.
Webb is, yes. The solar cells are on the hot side of the sun shield for obvious reasons. You'll hear about that next month. Then I actually am the speaker and Gary can introduce me for real.
Oh,
Sorry for stepping on your toes there.
sorry. Yeah, I'm sorry. Here we go.
No, no worries. No. I hope it was of sufficient accuracy to set things up.
Good means that's a topic I can ignore.
Unless there's an actual number for how many days they think it'll be in between having to readjust orbit. That's kind of an interesting number. I know I hadn't considered that that means they're fuel limited for sure.
Mhm. Yeah, James Webb has a minimum lifetime 5 years. They have to meet that. I think they're looking to meet maybe 10 years, but eventually they're just going to run out of attitude control fuel. And before they do that, they have to dump it into the graveyard orbit where, Herschel and Planck and everything else. I don't know what they're going to do when they fill up the graveyard orbit. No, it's a solar orbit, so it'll take a long time to fill it up.
Yeah. It's interesting. They've gone to so much trouble to design it so it doesn't need cryogenic stuff. It doesn't need liquid helium or liquid nitrogen.
Yeah, it's not supposed to, but last time I looked, I think it does have a cryogen on board. They designed it originally for cryogen, then they took the cryogen out, and I think they put it back in because the long wavelengths, 26 microns or so, even that far away from the Earth, you just have to do it. Spitzer did it, and then I think you're too close to the sun, you just have to do it. But I think they'll run out of attitude control fuel before they run out of cryogen.
Yep. It was crossing my mind. Well, you could put it in something like L4 or L5, but then looking into the distance, it's like, yeah, okay, sure. I don't know.
I have no idea which point is easier to get to orbital mechanically from here. I don't know that much about it.
Yeah, it's also so far away. It would take ages to get there, I'm sure, and get on station and get doing your thing. Yeah.
Yeah, and if there's dust or junk gathered there, it's probably the kind of environment you don't want to be in. I think that's not the case at L1, 2, or 3.
Yeah, it wouldn't. Yeah, it shouldn't be. They're unstable, so you shouldn't have lots of dust gathering. That
Yeah,
could really mess up an infrared telescope too.
Yeah,
Dust from
yeah.
That's
infrared.
the problem with L4 and L5 putting a telescope there, is that you'd be really worried about the dust.
Mm.
They flew Spitzer through one of them deliberately just to see if they could monitor the dust environment or something like that. I never heard of any result that came out of it, and I don't think it affected the imaging, but it just passed through. It didn't hang around, which is different.
Yeah.
I don't know if this will have any application with spacecraft eventually, but I saw an article today. I think it was at Purdue, but I might be wrong. Anyway, they invented supposedly the whitest paint that's ever been invented. And they made it because it's so reflective. And they said it reflects like 99 point something % of the sunlight that falls on it. But in the infrared, it actually emits more heat than what falls on it. And so it actually, it's cooler than its surrounding. It should cool whatever's behind it. At least that's what the article said.
Yeah, I don't know. I'll pick that up.
They were talking about it for houses and buildings, but it occurred to me, I wonder how long, I mean, it's not going to be very long before it gets dirty.
Yeah. And keeping it clean is costly, I'm sure.
Yeah, it'll cost a few extra $1 billion to make it space qualified like everything else.
Well, you know, they space qualified that cupola in 6 months. Uh, that's because NASA didn't do it.
Probably.
Uh, so they originally were going to do the Inspiration 4 just at the same height as the International Space Station. In fact, Jared is the one that said, how come we can't go higher? I mean, let's push the envelope a little bit. And the guy goes, well, when you push the envelope, you're introducing more risk. And the guy goes, okay, let's see if this risk is manageable, you know? And they said, let's do it from each system. And they sat down and they went over it, and they're saying, well, you know, how is this going to affect, you know, the communications? How is this going to affect the life support? How is this going to affect the return, you know? And they said it was very little difference between, you know, 400 kilometers and the 575. They ended up actually touching 585 before they circulated the orbit, but
Gemini 11 made it out to around 1,300 kilometers. It was 739 nautical miles at apogee. Apogee.
Yeah.
And nobody's beat that yet, and I don't think anybody will for a while. For
Yeah.
orbit, I mean, going to the moon, yeah.
Yeah. So.
Yeah.
I would have liked to have been on that Gemini space. Well, it's pretty crowded in there, you know.
Too bad.
The Gemini and the Mercury, you just sort of had to like put on those. It's like putting on.
Well, Mercury was just a chair sitting on top of a rocket, you know. I mean, it's like,
Yeah.
doesn't really amount to anything but a flying chair. Gemini was a little bit more. Yeah.
Well, I remember when SpaceX first started, and you didn't hear the name of Elon Musk or anything like that beforehand, really, you know. And I carpooled in with two guys that worked at the formerly Hughes, but then Boeing just bought them out, the satellites, and they actually built the satellites that went into orbit. And I worked at SBC or Pac Bell at the data center. I was the data manager. And I told them, I said, hey, there's this guy, he's putting up $1 billion and he's going to get another $1 billion, you know, from investors and stuff. And anyway, he's going to launch his own rockets. And they were in the back seat and they were both laughing. They're saying for $2 billion, you can't even buy the blueprints. You know, and I said, this isn't the government. This is private. I mean, you're trying to tell me $1 billion, you know, they're saying you got to build a launch pad. And I go, no, you just have to convert an existing launch pad. I don't think you need to build a brand new one. Although in Texas, he's building a brand new one, you know. SpaceX last year sent up just over 66% of all the mass that was launched last year. Right now, if you want to look at how many launches there were, China has launched more launches than SpaceX this year. But SpaceX, even though China has launched a main module of their space station, SpaceX has sent more mass into orbit. SpaceX has launched more into orbit than any other country on Earth, period, you know, in the last 2 years. So, and yeah, a lot of it's funding because NASA NASA says send our astronauts and they pay them for that. But at the same time, you know, most of the mass that went into orbit was not government funded. So because Starlink was the most mass. So, and It's not that I'm against ULA or anybody else. It's just that, get off your keisters and do something,
They're all working on it. I've been to SpaceX a few times, toured their factories. It's an efficient operation. They know what they're doing.
Yeah.
I'm impressed.
It-
I
it-
think that it's going away from governments. Governments are going to get out of the space business at some point. It'll all be private, just a matter of time.
Yeah. Yeah. And I believe you need the government involvement to kickstart this stuff, and because it's just there's too many unknowns, and the only things that can manage the unknowns is just like the web. I mean, it was unknown. We're saying, well, how much is this going to cost? Well, it's unknown, and it ended up costing a lot more than they anticipated. But that's because they're doing something for the first time. And, and usually for the first time, when you go to the moon or you do stuff like this, launch people to space, the governments do it because there's too many unknowns, and the only people that can handle the unknowns like that.
The only people who want to pay for it. Private industry doesn't like to pay for things they don't know are going to pay out immediately.
Yeah, there's not a big, huge return on investment for the Mercury space program,
Oh, the recording's still running, by the way.
Yes.
I don't know if you want to record the full end of the meeting.
Yeah. We're going to go ahead and stop the recording now. And first, we want to thank you very much. It was a very good presentation. I appreciate it. So thank you. And this will be on
Very good.
Facebook a little later tonight. Okay.
We all use clean language anyway, so there's nothing wrong with the recording.